Julle kan maar sit. Good afternoon, everyone. I think these are really one of my favorite events on the calendar. We always complain about student numbers, about not having enough time for research, about research funding, about lazy students. But this is really one event where we can just celebrate and be joyous. So tonight I welcome you to the inaugural lecture of Professor Ted Kroon. Professor Kroon, a special word of welcome to you. We are certainly looking forward to what you will present this evening. And with the maths, the same with the maths inaugurals, I'll try and keep up. I certainly learned a lot in these inaugurals. I'd like to welcome the Chair of Council, Mr. David Noko, who's joining us virtually. Then I'd like to welcome the Vice Rector, Institutional Change, Strategic Partnerships and Societal Impact, Dr. Malapo Kabela, who is also joining us online. The Dean of the Faculty of Natural Agricultural Sciences, Professor Dani Vermeulen. He's here, but apparently he has no voice, and his physician recommended that he does not speak, which is, I'm sure, for the faculty, quite an interesting phenomenon. So welcome, Dani. Then I'd like to welcome the Vice Dean of the Faculty of Humanities, Professor Chitwa Twala. I saw him at the back right at the end. Welcome, Chitwa. I'd like to welcome the Head of the Department of Physics, Professor Koos ter Blaans, who is sitting right here to my right. Welcome, Koos, and congratulations on this important event in your department. Then I've welcomed Professor Kroon shortly. So Professor Kroon, welcome to you too. We're looking forward to hearing what you have to say. And then I'd like to welcome Professor Hendrik Swart. Hendrik is standing in for the Dean. Hendrik, as far as I know, has a voice. So he will be able to introduce the speaker this evening, so we're looking forward to that. Thank you, Hendrik, for standing in. Then I'd like to welcome some family members of Professor Kroon. So first, his parents are here. His parents joined us this evening, Rory and Pam Kroon. And I think you're sitting in this row. If you can wave your hands, that's his family. Welcome to you. It's a privilege to welcome you on campus, and you must be so proud of your son. Then I'd also like to welcome Joy Kroon, who is Ted's wife. Joy, if you can raise your hand. Well, welcome to the university. And to his two sons, Dylan and Philip. There they are, colleagues. If you want to say hello to them, welcome. It's fantastic having you here. Then, of course, I'd like to welcome all the staff from departments outside of physics. Thank you for joining us this evening. Also, the students who are here, the staff from the Department of Physics, thank you for celebrating with us this evening. Then I'd like to introduce Professor Hendrik Swart, who will introduce Professor Kroon. Thanks, Hendrik.
First of all, good evening, everybody. It's not that nice to stand in front here with that lights in your eyes. You cannot see the audience, so we're talking to a blank audience here. So first of all, our dean lost his voice. You know, if you have grandkids, the chance to get sick is 99%. So he's a very good grandfather, and he played with his grandkids a week ago, and now he cannot speak. So bear with me tonight. I have to read his speech. It's not my own speech, it's his speech. So let me do it for you guys. Prof. Robin Edward Ted Kroon was born in Boksburg, attended primary school in PE and high school in Graafrenet Union High, where his father was a math teacher. He obtained all his degrees from the then University of Port Elizabeth, where he obtained his PhD in 2000 with the title Simulation of TEM Dislocation Loop Images in Ion-Implanted Semiconductors. After his postdoc, he started work as an application engineer for Corning Optical Fibres before joining the Department of Physics here at the UFS in 2003, where he was Program Director for Physical and Chemical Science from 2004 to 2011. Since 2006, he has focused his research on luminescent materials and phosphors. In 2014, he became an associate professor, and in 2019, a full professor. He was supervisor or co-supervisor of 8 doctoral students and 8 MSc students. He holds a C2 rating from the National Research Foundation, and he has published more than 150 articles and book chapters to obtain the Scopus H index of 25. Since 2016, he has been part of a collaboration project between South Africa and Sudan, funded by the African Laser Center to explore the potential of bismuth-doped phosphors. On a personal note, what he considered remarkable about the physics department is the combination of research in luminescent materials and astrophysics, which appear to be different looking from outside, but actually are so similar because both study light and use similar equipment and concepts. We just want to welcome our colleagues from Kwakwa. Glad that you can join us. At least I can see you guys. Now, in Ted's own words, in real estate, they say, if you buy a poor house in a rich suburb, its value will go up. And I am fortunate to have an office which is quite a mess in a fantastic department of remarkable colleagues. The topic of his lecture tonight is, what's the use of a rainbow? Everybody has seen a rainbow, and rainbows are familiar devices in literature, culture, and marketing. Far from being only a colorful spectacle with no practical value, rainbows are useful and lead to useful things. Tonight, we are looking forward to hear about the usefulness of rainbows. For a normal layman, the only useful aspect of the rainbow is that we know that we will find a pot of gold at the end of the rainbow. Hopefully, Ted will tell us how to reach that pot of gold. Ziad Abdelnour, the author of Startup, Saboteurs and Economic Warfare, said, "Do not turn around, do not look back, keep moving forward, keep pushing. The pot of gold is at the end of the rainbow, not at the beginning." We never know the beauty of the rainbow unless we see it. This is so very true for Ted, to keep pushing forward to the end of, and to receive this pot of gold in the form of a full professorate. Congratulations, Ted. We are really looking forward to your talk tonight. So good luck.
Thank you very much for those kind words and the welcome. I appreciate it, and welcome personally from me as well to all the audience, especially from my colleagues from Kwakwa and my family, and staff from other departments in addition to the physics family that I have. So I'm going to speak about the use of a rainbow, and let's get started with where the rainbow comes from. So there's a old African legend that says, in the beginning of time, God was creating all the animals of the grasslands. He crafted the beautiful gazelles, the sly hyenas, the elegant giraffes, and the proud lions. But he wished for one animal that was as colorful as the blooming flowers, the coral fish, and the shimmering birds. With these in mind, he created a zebra with stripes that were of every color which was of every color. But the other animals were jealous of the zebra, and the lions decided to hunt and kill them. And the zebras cried out to God to help. So God sent a big rainstorm to wash the colors out of the rainbow, out of the zebra, and leave it with the black and white stripes. But the color gets infused with the raindrops, and now when the clouds form, we can see the zebra colors in the rainbow. So I hope to change that story later on in my lecture, but it is a beautiful story. This is a photograph of a rainbow taken by one of my colleagues, Marie Duvenhagen, so she's given me permission to use it. And I feel it is a beautiful example, even though the rainbow is quite small and not too prominent. It's difficult to take a picture of a rainbow, the whole thing. If you take a small section, then you can get a very big picture. But a rainbow is a very large item, and she explained to me afterwards that this is a montage of a lot of photographs. But when you're looking at a rainbow, your heart leaps up when you see a rainbow. And I don't have to wait to see one in the sky. I see them every day in my research, and that's what I want to tell you about. So what's the use of a rainbow? I'm not the first person to contemplate that question. C. Day Lewis wrote in a book a long time ago. He explained a rainbow is a natural phenomenon, the result of refraction and reflection of the sun's rays in drops of rain. So he helps me out a bit there. We'll get to that. And he says, as far as mankind is concerned, it's a perfectly useless object. That I will take exception with. He says it won't help anybody make any money. And yet the poet who said, my heart leaps up when I behold a rainbow in the sky, put into words the feeling of wonder and excitement we all have when we see a rainbow, which I fully agree with. So let me illustrate some usefulness of a rainbow straight away. I didn't ask Marie exactly the circumstances of her taking this photograph, but I know that from my research that a rainbow has got an angular size of about 42 degrees. And so that's what I said, it's a large object. From the one side to the other side, it's 80 degrees, almost a right angle. And the anti-solar point, which is directly opposite the sun behind you when you're looking at the rainbow, is in the middle of that arc. And I also know that the Earth revolves at about 15 degrees an hour, and the anti-solar point here is about 15 degrees below the horizon, which means the sun on the other side was 15 degrees above the horizon, so it was about an hour to sunset. Also, because the sun was setting behind me in the west, when she took the photo, she must be looking east, more or less east when this, in this picture. So you can do some analysis with that. Of course, I could be completely the opposite, and she took it in the morning, but one of those two. So it could be just the exact opposite in an early morning photo. Now, this is a video I got off YouTube of somebody that saw the whole rainbow. We can only normally see half of it, but if you get up high onto a structure like a crane, then you can see the whole rainbow, and you can see the colors, and if you're lucky, you can see on the outer edges a bit of a secondary rainbow as well. There's a bit in the corner there. But I also want you to look at the shadow of the position where the photographer is standing, and you can see that concept that the anti-solar part, the sun directly behind him, is right in the middle of the whole rainbow. So at that point over there in the center of the rainbow is the anti-solar point. So another use for rainbows in South Africa, we are the rainbow nation, is we can express frustration in the rainbow, or also great celebrations when things go well. And the poet said that we're not going to make any money with rainbows, but I hope that these authors had better luck. They're all trying to sell books about rainbows, and so you can make a bit of money from rainbows. They're good for advertising, and that's why I used the concept to get you here this evening. And rainbows are everywhere in art, in culture, in religion, in entertainment. I knew I was going to get asked about where's the end of the rainbow for that pot of gold, so in advance I will say that in Stellenbosch there's Rainbow's End Wine Estate, and if someone is wanting to go check it out, I definitely come along and we can go look for the rainbow there. Yes. So I don't know if you can make money with rainbows, but you can lose money with rainbows, because this is not investment advice, but it's a Bitcoin rainbow price chart, and they've got the red part at the top saying sell, sell, and the part at the bottom saying buy, buy. Of course, they've got the wrong number of colors in the rainbow, and they don't have the right shape. It should be an arc, so definitely I don't know about taking this advice. Maybe it's good or maybe it's bad. And we can make some artificial rainbows with light-emitting diodes. So yeah, from the red color to the blue. So in our department, we have a lot of electronics. But I want you to actually focus on these resistors that are behind the light-emitting diodes here. And you will notice that they've got some stripes or colors on them. And what are those colors? Well, they are codes to tell you how much the resistor actually is, what is its value. And the color code is coded according to the rainbow. So from red, orange, yellow, green, blue, no indigo but violet, the colors of the rainbow representing numbers and giving us a scale. So the rainbow is useful in giving us a representation of value. And this is a slide that is taken from my research. And so my research is looking at luminescent materials. And this particular material that was being analyzed here was a calcium phosphate doped with an element called cerium. And what we want to do is we want to look at where it absorbs light and where it emits light. And I've got a false color scale over here. So there's my rainbow in my research. And two axes along the horizontal axis where light is being emitted and on the vertical axis where light is being absorbed. And you will see that this has got sort of a broad shape over here. And if you actually draw a graph through it, it's got two bumps which correspond to two energy levels of the cerium 3+ ion. And if you take a vertical cross-section, there are three prominent bumps, but another two on the side representing several energy levels to excite this material. Now, the colors here are completely artificial because this material actually emits ultraviolet light that you can't see. This is the wavelength that it is actually emitting, and the visible wavelengths only begin at about 400 nanometers, and this is emitting at shorter wavelengths. So it is definitely a false color, but a use of a rainbow in my research. These rainbow maps, when I was doing research for this particular lecture, I found out that the people that work with displays and things have got some negative comments about it, and the rainbow color maps are considered sometimes harmful. And the main reason why is they say these two graphs are representing exactly the same data, but one on a grayscale and one using colors. And they don't look exactly the same, but they are representing exactly the same data set. And the reason that they say it is difficult to understand sometimes these colored graphs is people can't put the colors into the correct order. So unless, if you go away from today, you should know the colors of the rainbow: red, orange, yellow, green, blue, indigo, violet, and then you would be able to say that this is the correct order and not green before yellow. But visually, we don't have a concept of that, and grayscales, we definitely know what order they should be in. But there is another reason for that, is if you get a picture like this in a publication, and then you print it on your black and white or grayscale printer, then you will only get this, and these are supposed to be the same data. It definitely looks wrong. So I have to think carefully about these color diagrams. But another place we can use colors is in so-called heat maps. And when we take a metal and we put it in a flame and heat it, it becomes red hot, and if it gets hotter, it gets even white hot. And we can make a scale of how hot the material is, going from red to yellow and almost white, based on how hot it is. And the reason it changes color is due to black body radiation, here on the bottom left. Again, there's a representation of the rainbow where the different colors of emission would occur. And the type or the place where the material emits in that, over that spectrum, where it emits most intensely, depends on its temperature and shifts from the red side to the blue side as it becomes hotter. But this can be very confusing, because if you then look at this chart over here, we know that red is a cool color, and then white is even hotter, and going across there, blue. But when we watch the weather or look on the internet, then suddenly we find that the cold areas are represented by blue. It's back to front. So we need to get the weather people and realize that red is actually cool, and the blue areas are the hot areas. But even the color people are confused, because, they say warm colors are orange and red, but cool colors are blue, and that's wrong. Okay, physics is wrong. Now we'll go a little bit out of my expertise and show a graph from astrophysics, but I said that that's one of the wonders of our department is that we can overlap with each other. And this is the Hertzsprung-Russell diagram that classifies stars in terms of their temperature and their luminosity. And again, we see a color scale and almost a rainbow of the different type of stars, their temperature and how much they are emitting. And at least the astrophysicists know that the blue side is much hotter and not the red side, so they've got it right. Now, I promised when I did the abstract for this that I would say rainbows can show stress. So here is a diagram of a protractor which is made out of transparent plastic, and when it's manufactured, it's left some stress in it. And if we view it through polarizers, so this is like from polarized glasses, and we view it through two crossed polarizers, we can actually suddenly get a rainbow of colors that reveals to us stresses in the material. So a rainbow can be there to reveal stress. You might say, I'm getting a bit cheating and getting far from rainbows, but we'll see the idea of polarization is also important in natural rainbows, so we'll get back to that. You even get materials called thermochromic materials that contain liquid crystals that we know very well from our television screens these days. Those are special crystals that have large molecules that have a twist in them, and the twist pitch can affect what light gets reflected, and this pitch is affected by temperature. So as these thermochromic materials change temperature, they reflect different colors of light, and so here we have something changing from only 38.7 degrees to 32 degrees, and our whole spectrum of colors. And this is actually a photograph of a thread that has been made. This scale bar is 1/10 of a millimeter, so this is maybe about 1/3 of a millimeter in size, and it can be used to knit and make clothes. Your clothes will tell you how hot or cold you are, or so forth. So it will be a beautiful rainbow-colored clothes. And this has got some practical applications in medicine. If we're worried about COVID, you can make out of these materials a thermometer, and you can see a rainbow can tell you whether you are feeling ill or if you are sick. And you can buy one of these thermometers to put on your gas cylinder, and when it is being used, the evaporation causes cooling, and you should see on the scale what is the level of gas and when you have to go and buy new gas. I don't have any commercial interest in this, and my brother tells me he's still trying to get his to work, so we'll see. You can also give it a try and let me know. So we also make phosphors to measure temperature. So I will show a few slides of work that I've done with many other people. Unfortunately, I cannot make an exhaustive list of all the many colleagues I've published with, and I do appreciate it. But I have got 1 or 2 snapshots of work that we do, and I was very happy with this work where we also used a phosphor to measure temperatures, and it will change its emission colors also based on the temperature. Or also how we excited it with long pulses or short pulses. So we look at a lot of ways in which we can change the color of phosphors to make rainbows in our department. Now, you can also need a rainbow to make a computer, because a computer is made out of silicon, and silicon is a semiconductor, but you also need to make regions that are not conducting between it, which we make out of silicon dioxide. So you have to have silicon dioxide grown on silicon, and based on its thickness, it changes, or the film changes color, so you can get a rainbow chart of how thick is the silicon dioxide layer on the silicon. And it's not only silicon, this is the metal bismuth that I'm very interested in, and it also forms an oxide on its surface and makes these beautiful colors based on the thickness of the oxide layer. So I'll talk more about bismuth later on. And then I would like to say that the internet runs on rainbows. That's not my idea, I got it from this book. Introduction to DWDM Technology, Data in a Rainbow. And DWDM stands for Dense Wavelength Vision Multiplexing. So you will notice that I did do a little bit of work for Corning Optical Fibres before I joined the University of the Free State, and I have to say something about optical fibers. And many wavelengths of light are passed along a fiber all joined together in a rainbow. So this picture is slightly misleading. It seems to show that the one has got blue in and the one is green and the one is red, but all the colors are combined in one fiber and all sent through cables between cities, even between continents and undersea cables, where they are taken apart again. So the data is being transmitted on a rainbow. Now, those are some examples, but I want to talk more about natural rainbows. And it gets a little bit of text here and a little bit more complicated. So I got this out of a review article on rainbows, which was published as recently as 2002. And it says a rainbow is a concentration of light rays corresponding to a minimum of the deviation or scattering angle. And then it says a rainbow is a caustic separating a two-ray region from a naught-ray region, or an integral superposition of waves over a cubic wavefront, or in part an interference phenomenon. I won't read further, but at least by the end of the lecture you should be aware of those four. I will go through them, and a few at the bottom we'll pick up along the way. So these are ideas or words that we'll throw around and try to get a better understanding of. So if you go to the internet and you say, how does a rainbow form, you'll find a picture like this. And it says there is refraction, dispersion, and reflection of light in a spherical raindrop. And you have the white light coming in, bouncing, reflecting against the back of the raindrop, and dispersing and forming all these colors. But it's not quite as simple as that explanation. And first I want to just say, forget about the colors. Let's just think about one color and the reason why the rainbow has got a size of 42 degrees. There must be a mathematical and physical reason for this. And if you go and do some calculation of light coming into a spherical drop, you find that the light comes out at a lot of different angles and not always 42 degrees. So the 42 degrees of the rainbow is really a puzzle. And this puzzled scientists for hundreds of years. In the 16th century, there were a lot of publications with very strange diagrams of how the light was being bounced around in the drop. Here's a beautiful one from Kepler, who is famous for the orbits of the planets, the elliptical orbits of the planets, and he thought that it must go around sort of the circumference, but no one really knew how it worked. And this problem was solved by René Descartes in 1637, and he did the work that I've just described. He looked at a lot of light rays coming in a raindrop, and he actually calculated the angle at which all of them would come out. And what he observed was something very interesting. Here's his table of data, is that the angle at which they come out has got a maximum in it. So these values are rather small, but yeah, it's 40, and then it goes to 41, and then it decreases again to 40. So there's a maximum there, and we're just talking about one wavelength, one color, not the colors of the rainbow, but just one color that is involved here. And this is a better description of what is happening, is if you go from the bottom and you draw these paths of the light, and you go up to a certain point, this red one, you get to some sort of value of where the deviation is a certain value. And if you go any higher and let the light go in, the ray lights sort of go back again to where they originally were coming from. So there's a maximum value in this deviation angle over here. And that we call an optical caustic. Caustic is interesting because caustic means burning, and it is similar to how light gets focused by a lens, but it's not the same concept. And the word lens also comes from, or the word caustic comes from the Greek for burning, whereas the word focus comes from the Latin for burning, so they've got a similar origin to each other. So this caustic is a place where the angle changes. And because of that, most of the light is concentrated there. And there's a nice physics analogy for this, is if you had to take a ball and throw it up and say, where does it spend most of its time in its trajectory as it goes to its highest point and comes down again? Now, I calculated that it spends 3/4 of its time in the top half of its trajectory and only 1/4 of the time in the bottom half. And the reason for that is when you throw it up, it's moving fast, but as it goes higher, it moves slower. So it spends a lot of time, and then it has to turn around at the top and come down, and it's still moving slowly near the top of its trajectory, and near the bottom again, it's moving fast. So it spends most of its time near the top of the trajectory. And in the same way, since the light that can come in here, it's being reflected in a lot of different directions, but it changes angle at this point. Most of the intensity is at that point of the optical caustic. And that angle corresponds to the 40 degrees that we measure for the rainbow. So you can regard each point or each droplet as emitting a cone of light, and not just at the angle of the rainbow, but everywhere inside that cone, but just mostly intense on the border. And this picture shows it very nicely. This was taken by a drone at Victoria Falls, and you can see the rainbow on the border, but you can see the region in the middle is also got like a whitish tint. That is because you don't only get a reflection from the rainbow at 42 degrees, but at all angles smaller than 42 degrees, just the maximum intensity on the edge of the border. So these come out then at an angle of 42 degrees, and if you want a drop to be reflecting within your field of view, you can form the same sort of cone in reverse, and you should see a rainbow with an angle of 42 degrees in the opposite direction. Any droplets that are within this cone of 42 degrees of your viewpoint will reflect light to you, and those that are outside that region, you won't be able to get light from them, so that it will appear darker. But a good physics theory can also predict things. And we've described a path of light where the light gets reflected once in the drop, but you can also have light coming in and getting reflected once and then twice and then coming out. And a wonderful thing happens is that whereas in this analysis there was some sort of a maximum value for the angle, yeah, if you follow the paths, there's a minimum value for the angle that the light can come out, and it leaves a little gap where no light is reflected from either having one bounce in the droplet or even two. And this region over here is then very dark, where we can see a rainbow in this region and a rainbow in that region, the secondary rainbow. And this is called Alexander's dark band. And you can see everything is reversed order, because this one is making a maximum angle, this one is making a minimum angle, both making caustics but in opposite sense to each other. So here is a photo of Alexander's dark band with the brighter region inside, and the secondary rainbow with reversed colors, and again a bit more brighter here than in the dark band. And this is the visualization I'd like you to think. Of course, it must be a full three-dimensional drop, but the primary rainbow reflects anywhere in the central cone up to 42 degrees, that is this region over here. Then there is the Alexander dark band where no light is reflected, and then there is the secondary rainbow that will reflect everywhere in this region, but most intense at this angle over here, because that's where its caustic lies, giving you the secondary rainbow in reverse. So what about the colors? We have to discuss them as well. They are, after all, everything that people know about the rainbow. I just was explaining where the angles come from. So the rainbow's got a little bit of a size, and that is due to what we call chromatic dispersion, where the different colors get bent different amounts when the light goes from the air into the drop. And they get bent more for the blue light than for the red light. That means that this bending process is more strong for the blue light, and its angles are small. Its caustic occurs at a smaller angle, and so here's a graph of different wavelengths that we might get from red light to blue light, and the angle of how much light intensity. The brighter regions is where the caustic is, but it doesn't go completely dim, and you can see that the caustic angle for blue light is at a smaller angle than for red light, and that explains why it is separated into the colors and the order of the colors. Also notice that although we like to think about the rainbow as beautiful colors, they're very impure. The red might be pure because nothing overlaps it, but the green has got some red also, because this is where its caustic is, but it's reflecting any angles that is smaller than that. So some of this red joins with the other colors over here. So the blue is very impure, whereas the red is quite pure. So a droplet doesn't make a very pure rainbow. And then another point to note is that we've been talking about one drop, but when we are looking at a rainbow, we are seeing many, many drops, and from each drop we're seeing only one angle. And so we're seeing the color that's relevant for that angle, and we're seeing different colors in different raindrops. So nature is not stingy. Every single drop of rain makes a rainbow. And we can only see every drop at one particular angle. And all of those drops come together to give us how we perceive the rainbow out of those all the drops that are making each individual rainbow by themselves. So I said you would be able to see more of a rainbow if you came here, and I've got a photograph of somebody that, a picture of somebody that took a photograph of a rainbow in the ultraviolet and in the infrared. So you can see past the red, we can see the infrared and the ultraviolet. So the rainbow is broader than what we give it credit for, as long as you can have a camera that can see the different wavelengths outside the visible spectrum into shorter wavelengths or longer wavelengths. And this has got practical applications. You can see that the rainbow it's how it works is very critical on the refractive index, how much the light gets bent. And so we can use this concept to actually measure refractive index of liquids by putting them either in a droplet or in a cylinder which mimics a sphere. And I was amazed to come across this paper, because in our department there's one student, Lucas Erasmus, that must do some work based on refractive indexes, and we discussed ways of trying to measure it. And this was a technique I was not aware of that can measure it to 1 part in a million. So that's a very accurate refractive index measurements. And then I noticed you can even measure the temperature, because the refractive index of a liquid depends on its temperature as well. And I love this photograph of a rainbow taken on a ship. It seems like the rainbow gets a bit out of joint in this part over here, but this rainbow is taken of the clouds in the background, and this is in the sea mist, and the sea mist has got salt in it, and the salt makes the refractive index larger, and that makes the refraction more and makes the rainbow radius smaller, so slightly smaller. So you actually are seeing that this is salty water compared to pure water that's making the background rainbow. So I said we'd talk about repolarization again when we discuss those stress patterns, and it turns out that the rainbow is polarized. So there is something called the Brewster angle, and the Brewster angle is a special angle at which if light is incident on a material at that angle, then the reflected light is polarized, and that means that light is oscillating in certain directions, and when it's polarized, it's only oscillating in one direction. And the light that comes in, if it's at the Brewster angle, the light that's reflected will be polarized. Unfortunately, this is not the light that's making our rainbow. It has to go in and come around, bounce once and come out. But it turns out that if this is close to the Brewster angle, then this angle is also close to the inverse Brewster angle, because now we're moving from inside the drop to trying to go outside of it, which also causes a polarization effect over there. And this light that eventually comes out of the rainbow is complete, or almost completely, not completely, but almost completely polarized. I've got a video of somebody putting a polarizer in front of the rainbow over here. So the polarizer will only allow through certain directions of oscillation, and you can see at the rainbow we can see less of it or more of it. It's always still there, but you can make it disappear based on its polarization. This has got an amazing application that I learned of. This is a paper that was written about trying to find habitable planets, and they say that we might be able to use rainbows to see if planets have got water on them. And this has actually got some old research where they used rainbow scattering of the clouds of Venus to figure out that the clouds in Venus were not made out of water but out of sulfuric acid. And the way they can do that is based on the polarization effects of the light and how it depends on the refractive index. So this is a graph here of how much is scattered and the refractive index, and they surmise that the material that it could be made out of in Venus is sulfuric acid. And when the Russians sent a spacecraft there, it was confirmed. Here on Earth we're dealing with water, and on Titan from the clouds you can see that it rains methane. This is also being used to monitor the clouds on Earth by satellites, because it is also important for us to know whether clouds are made out of ice or water droplets. And ice does not have the polarization effects that the water droplets do. So these satellites can look at the clouds from above, and based on their polarization can find out whether they're made from water or from ice. And I suppose that might be used for researching global warming and things like that. There's another interesting part of the rainbow, sometimes you see it, are these extra lines that form on the side called supernumerary arcs. And up to now, the whole theory of the rainbow hasn't depended on how big the droplets are, but the explanation for these extra arcs are due to interference. And Thomas Young, he was one of the first person to believe that light was a wave, and waves undergo interference. And what he said is that we have this picture here of the light coming in and of the special angle of this rainbow ray of the maximum deviation, and then it forming a caustic and coming back. But he says because it comes back, you've got more than one ray over here, so there can be interference of the rays, and when you get interference, you can get constructive or destructive interference, so you have these bright bands and dark bands forming on the edge of the rainbow, the supernumerary arcs. This was taken even further a few years later by an astronomer, Airy, who added diffraction to the mix. So what is diffraction compared to interference? Well, diffraction is when light bends around corners, and this is a picture of somebody holding a ball bearing, and you can see these fringes over here that are caused by diffraction. And what he did was he followed the wave path of the light through the raindrop, and notice that the wavefront was originally flat when we consider the wavefront flat before it enters the raindrop. It sort of forms a bent region at the caustic, a fold of the diffraction pattern, representing the wavefront, sort of the two waves that can interfere with each other. And he was able to mathematically trace this folded wavefront back and show that it originated in a cubic form, and then from that cubic form projected forwards to figure out the diffraction pattern that the rainbow should have. And there's a lot of mathematics involved with that, and we won't get into that. But Airy got an interference pattern that was similar to Young's, which also showed interference. But what was important of Airy's model is it showed that some of the rainbow light could even go past the caustic into the dark band, and so it affected the region where the maxima occur, the rainbow angle. And if the rainbow occurs at the rainbow angle, or where Airy predicts, it's a difference of about a degree, which was big enough to actually be able to be measurably important in terms of understanding the physics. There's another theory of the rainbow that takes it even further than that. It's called mi-scattering, and that regards light as an electromagnetic wave. So there's a sort of a saying that says God said in some equations and there was light. Those equations are Maxwell's equations for electromagnetism, and they describe then how light and other electromagnetic fields work. And one can consider using these equations instead of just light and optics concepts to figure out how the rainbow will form. And it turns out, so there's a lot of models over here, the Descartes model where we just had the rainbow angle and the caustic, and then it sort of goes down. The Young model that showed some interferences, but the positions are wrong. Then the Airy model where the positions where it entered into the Alexander dark band and the positions were correct. And then the Mi theory has got these extra interferences on them, so it seems to be very, very complicated, and I'll try and give you a sense for why that is. And then there's another theory, the Debye theory, that came later, even though it's listed above there, which I will allude to in a moment. So where do these extra interferences come from? Well, when light falls on a raindrop, we've discussed the light that goes in and gets reflected from the back surface and comes out. And if you're not at the rainbow angle, you can have sort of two different regions where the light can come in and come out at exactly parallel to each other, and those two can interfere, and they cause these supernumerary arcs. But these supernumerary arcs have got a fine detail in them, and they are due to extra reflections. Reflections of the light that can come in straight and reflect off the drop and come down, and it's parallel to the original two rays that are coming out. Or light that came onto the edge and came around and comes out parallel to the light that is coming out on those two rays close to the rainbow angle. And these are all very sensitive to their phase differences, and so the pattern that is formed is critical for how big the drop is. and even if it is spherical. So it allows us to very accurately work out things about the drop. Now one can do a Fourier transform of this scattering angle and all the peaks, and wherever there's a frequency you will get a peak in the Fourier transform, and yeah, at some low frequencies you will get the supernumerary arcs, which are very far apart at a low scattering angular frequency, and then these fine details form extra peaks over here due to these other reflections that we have. And these can be monitored in real time in a setup where you have a laser beam in a spray to figure out how big the droplets are, what are their size distribution, and so forth. And I had a student who did some work on using a nebulizer to make a layer of graphene oxide, and the applications for this is in many things: fuel injection, spray coating, spray cooling. And we're pleased that the student won a prize for the publication at the latest South African Institute of Physics conference. Now, I said that my scattering had all those complications. The last theory that I'm going to discuss is the Debye series, and that was a way of taking the my solution and just breaking it into, so it's the same solution, but breaking it conceptually into where it corresponds to the light that has come into the droplet. The light that has just been reflected straight off the droplet, gone in and come out again, been reflected and come out, or gone and been reflected a second time, and you will see this P equal to 2, or the red part is corresponding to our primary rainbow, and this blue part with labeled P equal to 3 would correspond to what we would normally think of as the secondary rainbow. And this graph over here is showing in angular form the intensity of the light from all these different rays that are coming from the rainbow. And it is a much more sophisticated version of this very simple picture I showed you earlier on, with this cone in the front, with the primary rainbow is now represented by this red band, with not only the rainbow angle, but all the supernumerary arcs that occur in it. And the secondary rainbow, this region over here, is corresponding to this blue part that extends all the way back behind the middle point where the drop is situated. So the red and the blue represent this picture. And you've got, in addition to that, not only the primary and secondary rainbow, but also the tertiary, quaternary, quintary, and all the other higher rainbows that can form from the light moving around in the drop, and how big are their intensities. And it's very interesting, the next two in this diagram, P equal to 4 and 5, the gray one and the pink one, they are in the opposite direction to the red and the blue one. They're pointing the other direction. So if you want to see those rainbows, you have to look towards the sun. And they are also, if this is about 40 degrees away from the antisolar point, these rainbows occur at about 40 degrees to away from the sun, and due to the sun's glare, they're almost impossible to see. Now, people have said through many years that they've seen these rainbows, but it has only been, sorry, I've got a chart. Here's our primary and secondary rainbow. The person's looking the wrong way, the sun's coming from that side, but he's interested in seeing the tertiary and the quaternary rainbows, which are on the opposite side to the normal rainbows, towards the sun over there at, again, about 40 degrees. So the first photographic evidence for these was only published in 2011. So that is very, very recent for rainbow research. Now, I can see it, I hope you can, that there's a little band of color. It's a color-enhanced photograph. The sun is somewhere behind this tree, and we're looking at about 40 degrees away from the sun itself and not the antisolar point. So this was very much enhanced, and it was the third order rainbow. And this one you say, I can see it very easily. That's not the third order, this one I want to talk about is the fourth order rainbow, and it looks like you can see it quite easily, but that's not the fourth order rainbow, that's the third order rainbow again, and this little band of light that's on the side here is actually the fourth order one. I'm not sure if you can see it. I've looked at these pictures a lot, and yes, but a lot of enhancement of these photos to try and see, but I think it's a marvel of physics that from the theory you know exactly where to look, and when you look there you can with very great care find something that no one has seen before. There are even people that have found the fifth order rainbow, and I like this title of this article, probable photographic detection of the seventh order one. You might happen what's happened to the sixth one. Well, I hope that you might want to find it. This is the normal picture of this finding the fifth order one. The actual color enhanced one's got a little bit of a green tinge over here, and that green tinge is the fifth order rainbow. So let's come back to this slide about what is a rainbow. I hope that I might have convinced you that it is a concentration of light corresponding to a minimum deviation angle or scattering as a function of the angle of incidence. I have mentioned that it is a caustic separating a 2-ray region from a 0-ray or shadow region, which is the Alexander dark band. From the Airy analysis, it's an integral superposition of waves over a cubic wavefront. And it is an interference problem from Thomas Young. Also, we skip a few because they're very mathematical. It is defined to a considerable extent by the behavior of the third term in a Debye series expansion of the Mie scattering. So that corresponds to that p equal to 3 value. And let's go back there, not too far. This p equal to 2 value, this value of the primary rainbow, its analysis, so out of the Debye series made from the Mie analysis. And yeah, so from the third term, the reason for the third term there is it starts at 0, so 0, 1, and 2. So the 2 is the primary rainbow. Quite confusing, the numbering. And then it is a polarized circular arc, and it is a fold diffraction catastrophe. I love that one. The wavefront is folded. For me, a rainbow is a water droplet solar spectrometer. So I work with spectrometers to analyze light, and the rainbow for me is a natural example of this. And I want to discuss that a little bit more. But in terms of Mie scattering, it is very interesting to know that the theory we use to discuss the rainbow, Mie scattering, is exactly the same mathematics that we use to discuss the scattering of light from metal nanoparticles, nanoparticle in size. We have exactly the same formulae. These are the Mie formulae for the scattering of light, which are applicable to rainbows and to nanoparticles of metals. So it is wonderful to see how two different things can come together. So you get a rainbow color of nanoparticles that scatter light at different wavelengths. These are nano-silver rainbows, not my own work. And this is some pictures of individual nanoparticles scattering light. This article's title was Single Silver Nanoparticles as Real-Time Optical Sensors with Zeptomole Sensitivity. And I had to go look up what zepto was, because it's one of those SI prefixes like milli, micro, nano, pico, but it's so far down the scale, 10 to the minus 21, that few people have heard of it, showing how sensitive the technique is. So we've also done some calculations on silver and gold and palladium nanoparticles, and then there had to be some gold in the pot at the end of the rainbow, so there it is. And I've had a postdoc and students that have tried to use metal nanoparticles to enhance the emission of phosphor, the light from phosphor materials, so that is something we've been interested in. The last sort of idea I want to bring to you is that we can do much better than a water droplet to make a spectrometer. So a prism does a better job, and there's something else, a diffraction grating, which does even a much better job than a water droplet. And the diffraction gratings make much, much better rainbows. And there is this quote from J. Strong. It is already 60 years old, but he says it is difficult to point to another device that has brought more important experimental information to every branch of science than the diffraction grating, because it makes these great rainbows. To the physicist, astronomer, chemist, biologist, metallurgist, we all use it to create rainbows and study them. So the surface of the diffraction grating consists of lines with equal spacing that give interference patterns that give us the rainbow. We won't go into that, but that's how it works. And you can use a CD as a diffraction grating. So if you reflect the sun's light in a CD, you can make your own rainbow, and you can actually take a picture of sun through a diffraction grating, and then you can get this beautiful picture. I don't think you've ever seen a rainbow that looks quite like that. So this is the company that makes this. It's a camera fitting, so it is an attachment for the front of your camera, a diffraction grating, and you can buy this photographic filter that makes these beautiful rainbows. If you can make better rainbows than from the droplet, you can see a lot more in the sun spectrum. So this was actually entered into a photographic competition. It is using a CD as a diffraction grating and looking at sunlight. And you can notice that there are some dark lines in them. They were first discovered by Fraunhofer more than 150 years ago, and they correspond to elements that are absorbing some of the sun's light in the Earth's, in the sun's atmosphere. So they are dark lines because some of the light has been absorbed. If you just look around the perimeter of the sun, you can actually see emission of light from different elements in the sun's atmosphere, corona. And so you can take a picture of the sun during an eclipse. They call it a flash spectrum, and you can get a beautiful new type of rainbow, different to the one we get from the water droplets. I love this one, but this one's got more science in it. You can see these lines at certain values where light is being emitted. And that one of those lines was incredibly important. These lines over here, they are in sort of the orange-yellow region. And if you do it very carefully, they correspond to some peaks over there, which have been enlarged. And this one on the left, enlarged here, comes from helium. And helium was discovered in the sun and not on Earth. From this line, they looked at the sunlight and they couldn't find any element that gave out the same type of emission. So helium is named after the sun, Helios, and helium was discovered then. It took 20 years before they found helium on Earth to verify it as an element. This is important for the Free State because helium deposits have just been found in the Free State near Virginia, and helium is in short supply, and it's very important for both medicine, where it's used to cool MRIs and things like that, and also for a lot of science. So helium in the Free State could be a really big deal. So it was found on the sun, then it was found later, but now it's been found in the Free State. That's good news for us. Rainbows can even tell us something about the whole universe, how it started and where it's going. Because these are rainbows made from distant galaxies. And we can see these dark bands in them, but they shift position. And that can tell us some idea of how fast these galaxies are moving. And it turns out that the further the galaxy is from us, the faster it's moving, which is the idea of why we believe the universe is expanding. And then if you take that backwards, why we believe that originally sort of was all at one point and we had the Big Bang. So rainbows can tell us many interesting things. I've been using rainbows to study bismuth luminescence. I've showed you the picture of the beautiful colors of bismuth, but we don't look at these colors. We put the bismuth ions into a lot of different materials we call hosts, and we study each of them, the energy levels, where they can absorb light, where it can emit light, to try and get a better understanding of bismuth as a luminescent material. And hopefully one day bismuth has got a commercial application like the cerium as a luminescent material. This is a good time to especially note Prof. Swart, who introduced me. I'm really glad that he had the opportunity. Sorry, I had nothing to do with the voice disappearing. But Prof. Swart is my mentor. He's a mentor to many people. And he's given me so many opportunities. So it was special for me that he could introduce me. There's even people that want to track the rainbow. So what they've done is taken a lens and put gold layers on it, and they believe that they've tracked the rainbow in certain regions, and they can use this for data storage. That is an interesting concept, but I mention it because this idea of how the rainbow gets trapped, the light rainbow, is exactly how your ear works. And they talk about waves in the cochlea, your ear, and acoustic rainbow sensors. So we might have a whole new type of sensors, and how your ear can hear different frequencies corresponding almost to the different colors of the rainbow. So how does your ear do that? It is based on the rainbow principle. And then for the astrophysicists, we only discovered gravitational waves a few years ago, but already there are gravitational rainbows at play. So life is interesting, and there's a lot to do. So many thanks to my family and colleagues, to the Department of Physics, especially to Prof. Swart, and the funding policies that make it all possible. And For me, rainbows, no rain required.
So, Ted, thank you very much for a really colorful lecture at a very colorful event. So I always want to say that. You've given me the perfect opportunity to use those words where it really means something. Now, I know I don't have much time and that you are all waiting for something to eat and to get out of the venue to have a discussion with Ted, but allow me to say something about Ted. Ted have a really colorful life. First of all, when I get, and I'm a morning type of person, when I get at the university, when the sun is still red coming up, Ted is there. In the afternoon when I'm leaving and the sky has turned blue, still with the rainbow colors, Ted is still there doing some work. So Ted, that speaks of someone with really, really dedication, and it's a privilege for me to working with you. And I'm really privileged having lots of discussions with you, which are sometimes really colorful, and I learn a lot from you as well. So you are also a special person in the department, and you are one of the persons that I will really take with me when I have to go to war. So I'm really glad to have you along me. I don't know what we're going to do, maybe lasers or something in the war, but that is something for another time. Then I know you also have a really colorful family, and I know you and your family also enjoys a lot of colorful things, like the birds that he takes pictures of, which are also really, really colorful. And I also enjoy seeing them on Facebook from time to time as well. So with that, I would like to invite all of you on behalf of, I have to say something last. Someone asked this morning in the Ethereum, they would like to enjoy a TED Talk. You have done it tonight. So there's a TED Talk. Okay, I have to put that one out there as well, Ted. So with that, I would like to invite you on behalf of Ted to some refreshments in the back. But before you get up, all of you, I'd like Ted and his family to go and stand there at the exit so that we can all congratulate on this occasion's event that you have brought on us. Thank you, Ted. Ted.